Hello and welcome to The Calm Scientist. Tonight, we embark on a journey to the very edge of our understanding, to the most enigmatic and awe-inspiring objects in the cosmos, black holes. These celestial giants, regions of space-time where gravity is so strong that nothing, not even light, can escape, hold the potential to unlock the deepest mysteries of our universe. Over the next hour, we will count down the top 20 ways these cosmic behemoths could reshape our perception of reality, from the nature of time itself to the very origins of our existence. So find a comfortable position, close your eyes and allow your mind to drift as we venture into the heart of darkness, where the secrets of the universe lie waiting. Top 20. The information paradox, a cosmic glitch in reality. We begin our countdown with a puzzle that strikes at the very heart of physics, a profound contradiction that has puzzled scientists for decades, the black hole information paradox. To understand this paradox, we must first journey back to one of the most fundamental principles of quantum mechanics. This principle states that information can never truly be lost. It can be rearranged, scrambled, or hidden, but the fundamental details of any physical system, its quantum information, should always be preserved. Now, let's turn our attention to the work of the legendary physicist, Stephen Hawking. In the 1970s, Hawking made a startling discovery. He found that black holes are not entirely black. Due to quantum effects near the event horizon, the point of no return, black holes should emit a faint glow of thermal radiation, a phenomenon now known as Hawking radiation. This radiation causes the black hole to slowly lose mass and, over an unimaginably long time, to eventually evaporate and disappear completely. Herein lies the paradox. If a black hole evaporates, what happens to the information of all the matter that fell into it? The Hawking radiation it emits appears to be random, carrying no details about the objects that formed the black hole in the first place. Imagine tossing a book into a fire. In theory, if you could collect every single particle of smoke and ash, you could reconstruct the information contained within that book. But with an evaporating black hole, the information seems to vanish forever, erased from the universe. This directly contradicts the core tenet of quantum mechanics, that information cannot be destroyed. This information paradox creates a deep and troubling conflict between two of our most successful theories of the universe: Einstein's theory of general relativity, which describes gravity and the large-scale structure of the cosmos, and quantum mechanics, which governs the bizarre world of atoms and particles. The resolution of this paradox is one of the most significant open questions in theoretical physics. Some scientists propose that the information isn't lost but is somehow encoded in the outgoing Hawking radiation in a very subtle way we don't yet understand. Others suggest that the information might be stored in a remnant, a tiny, stable object left behind after the black hole evaporates. And then there are more exotic ideas, such as the possibility that the information escapes into a baby universe, a new cosmos spawned from the black hole's singularity. Unraveling the information paradox is not just an academic exercise. Its solution could lead to a profound new understanding of how our universe works at its most fundamental level. It could be the key that finally unites general relativity and quantum mechanics into a single, elegant theory of everything, quantum theory of gravity. By studying these cosmic enigmas, by wrestling with the questions they pose, we are forced to confront the limits of our knowledge and push the boundaries of science into uncharted territory. The information paradox, our number 20, is a stark reminder that even in the darkest corners of the universe, there are profound secrets waiting to be illuminated. As we contemplate the profound mystery of information at the event horizon, let us now journey deeper, conceptually, into the heart of the black hole, to a place where our understanding of the universe completely shatters. This brings us to number 19 on our list. Probing the singularity, the breakdown of physics. At the very center of every black hole, according to our current theories, lies a singularity. It is a concept that is almost impossible to truly comprehend. Imagine all the mass of a star, sometimes billions of times the mass of our own sun, crushed down into a region of zero volume and infinite density. Here, at this single, dimensionless point, the gravitational pull is infinitely strong. Within the framework of Albert Einstein's theory of general relativity, the singularity is the inevitable endpoint for all matter that crosses the event horizon. It is a place where space and time, as we know them, cease to have meaning. The elegant equations that so perfectly describe the orbits of planets and the bending of starlight simply break down, yielding answers of infinity, which to a physicist is a clear signal that the theory has been pushed beyond its limits and a new understanding is required. This breakdown is not just a mathematical curiosity, it represents a fundamental frontier in our knowledge. What truly happens at the center of a black hole? Does matter truly get compressed to an infinitely dense point? Or does some new, unknown physics take over? This is where black holes serve as the ultimate crucible for our theories. They create conditions of gravity and density so extreme that they cannot be replicated anywhere else in the cosmos. Many physicists believe that the answer lies, once again, in a theory of quantum gravity. Such a theory would unite the macro world of gravity with the micro world of quantum mechanics. It would, in theory, allow us to peer into the singularity and see what is truly there. Instead of an infinitely sharp point, we might find a quantum foam, a turbulent, energetic state of space-time where the very fabric of reality is in flux. Or perhaps it is a state of matter so exotic we have not yet even conceived of it. The challenge, of course, is that singularities are cloaked by the event horizon. The physicist Roger Penrose proposed what he called the cosmic censorship hypothesis, which suggests that every singularity is hidden from the rest of the universe in this way. We cannot directly observe it. However, by precisely studying the properties of black holes from the outside, their mass, their spin, their effect on nearby stars, and the gravitational waves they produce when they merge, we gather the crucial data that can test the predictions of these new, more advanced theories. Therefore, the singularity is more than just a theoretical endpoint. It is a signpost, pointing the way toward a deeper layer of reality. It tells us, unequivocally, that our current picture of the universe is incomplete. By striving to understand this single, enigmatic point, we are driven to develop the next great revolution in physics, one that could finally explain the fundamental nature of space, time, and gravity itself. The singularity, that point of infinite density, represents a wall that our current physics cannot penetrate. It signals that our most successful theory of gravity, Einstein's general relativity, is incomplete. This forces us to seek a new, more profound understanding, and black holes themselves are the very places we must look to find it. This leads us directly to number 18. The singularity, that point of infinite density, represents a wall that our current physics cannot penetrate. It signals that our most successful theory of gravity, Einstein's general relativity, is incomplete. This forces us to seek a new, more profound understanding, and black holes themselves are the very places we must look to find it. This leads us directly to number 18. 18. Testing the no-air theorem. How simple can a monster be? At first glance, a black hole might seem like an object of unfathomable complexity. It is, after all, the remnant of a collapsed star, a chaotic and violent process, and it can swallow entire solar systems worth of matter, each with its own intricate history and composition. And yet, one of the most elegant and startling predictions of general relativity is that black holes are, in fact, the simplest macroscopic objects in the entire universe. This idea is encapsulated in what physicists whimsically call the no-hair theorem. The theorem states that once a black hole settles down into a stable state, it can be described by just three, and only three, externally observable properties: its mass, its spin or angular momentum, and its electric charge. All other information about the matter that formed it or fell into it, whether it was made of hydrogen, iron, old spaceships, or intergalactic dust, is lost forever behind the event horizon. The hair, representing all these other complexities, is shaved off, leaving a perfectly smooth, simple object. This is a profound and testable prediction. It means that if you know these three numbers for any black hole, you know everything there is to know about its external gravitational and electromagnetic fields. It doesn't matter how it was formed or what it has consumed. This provides us with a powerful tool to test the limits of Einstein's theory. In recent years, we have developed unprecedented ways to measure these cosmic giants. By observing the orbits of stars whipping around the supermassive black hole at the center of our own galaxy, we can make incredibly precise measurements of its mass. By analyzing the gravitational waves, the ripples in space-time emitted when two black holes merge, the LIGO and Virgo observatories can determine the mass and spin of the initial and final black holes with stunning accuracy. The data from these mergers allows us to perform a direct test. We can measure the properties of the two original black holes before they collide, and then measure the properties of the new, larger black hole that results. According to the no-hair theorem and the laws of general relativity, the mass and spin of the final black hole should be exactly what is predicted from the initial two. So far, every observation has confirmed Einstein's theory. Every black hole we have studied appears to be perfectly bald, just as the no-hair theorem predicts. But physicists continue to look for any tiny deviation, any hint of hair. Finding that a black hole has some other property, some other characteristic not accounted for by mass, spin, and charge would be a revolutionary discovery. It would be the first sign that general relativity is not the final word on gravity. It would tell us that there is new physics lurking in the extreme environment of the event horizon, and it would provide the first crucial clue on the path toward that all-encompassing theory of quantum gravity. The remarkable simplicity of black holes as described by the no-hair theorem provides a powerful way to test our understanding of gravity. For decades, however, these tests were indirect, relying on the subtle movements of distant stars or the faint ripples in space-time. The ultimate challenge remained to actually see one of these cosmic monsters, to capture an image of the very edge of reality. This brings us to number 17. Imaging the event horizon. Seeing the unseeable for most of scientific history, capturing a picture of a black hole was considered an impossible dream. By its very definition, a black hole is a region from which light cannot escape. How, then, could you possibly take a photograph of something that is fundamentally invisible? The answer, physicists theorized, was not to look for the black hole itself, but for its shadow. Imagine a bright light source placed behind a dark object. You don't see the object directly, but you see its silhouette, its outline against the light. In the case of a black hole, the light source is the incredibly hot, glowing plasma of gas and dust that gets trapped in its gravitational grip. As this matter swirls around the black hole at nearly the speed of light, friction heats it to billions of degrees, causing it to shine brightly across the electromagnetic spectrum. According to Einstein's theory of general relativity, the immense gravity of the black hole would warp space-time so dramatically that it would act like a lens, bending the light from this glowing material around it. This would create a bright ring of light, framing a dark central region. This dark region is the black hole's shadow, a direct visual imprint of the event horizon itself. The theory made a very precise prediction about how large this shadow should be for a black hole of a given mass. Turning this beautiful theory into an actual observation was a monumental feat of human ingenuity. The target black holes, like the supermassive one at the center of our own Milky Way galaxy and an even larger one in a distant galaxy called Messier 87, are incredibly far away. From Earth, their shadows would appear so small that trying to image one is equivalent to trying to photograph a single orange on the surface of the moon. No single telescope could ever have the resolving power to see such a thing. The solution was the Event Horizon Telescope, or ET. The ET is not a single instrument, but a global network of radio telescopes, spread across continents from Hawaii to the South Pole, all observing the same target at the exact same time. Through a technique called interferometry, the data from all these individual dishes can be combined, creating a virtual telescope with a diameter nearly the size of the Earth itself. After years of observations and painstakingly processing petabytes of data, the ET collaboration made a historic announcement in April of 2019. They released the first, ever direct image of a black hole and its shadow, the gargantuan beast at the heart of the Milky Way galaxy. The image was breathtaking. There it was, a fiery, glowing ring of light, slightly brighter on one side as predicted, surrounding a perfectly dark circle of pure blackness. This image was far more than just a scientific curiosity. It was the first direct, visual evidence for the existence of black holes and their event horizons. It turned an abstract mathematical concept into a tangible, observable reality. Furthermore, the size and shape of the shadow matched the predictions of general relativity with incredible precision, providing yet another resounding confirmation of Einstein's theory in the most extreme laboratory the universe has to offer. By seeing the unseeable, we opened a brand new chapter in our exploration of the cosmos. The image of the event horizon showed us, in stunning clarity, how the immense gravity of a black hole can bend the very fabric of space, turning light itself into a ring. But Einstein taught us that space is not a solitary entity. It is woven together with time into a four-dimensional fabric called space-time. If a black hole warps space to the breaking point, it must do the same to time. This profound realization brings us to number 16. Extreme time dilation, the elasticity of the moment in our daily lives on Earth. We experience time as a steady, unchanging river, flowing at the same rate for everyone. But this is an illusion born of our weak gravitational environment. General relativity tells us that gravity is not just a force pulling things together, it is the curvature of space-time caused by mass. And where space-time is curved, time itself flows differently. Clocks closer to a massive object tick slower than clocks further away. We can measure this effect, even here on Earth. Precise atomic clocks placed at sea level tick ever so slightly slower than identical clocks placed on top of a mountain. Our GS satellites, orbiting high above the Earth in weaker gravity, must have their internal clocks adjusted to run slightly slower than those on the ground, otherwise the system would lose accuracy within minutes. But near a black hole, this effect, known as gravitational time dilation, ceases to be a subtle correction and becomes the dominant feature of reality. As you approach the event horizon, you enter a region of such intense gravitational curvature that time begins to stretch dramatically relative to the outside universe. Imagine a thought experiment. You decide to journey close to a black hole in a resilient spaceship, while a companion remains far away, safely observing from a distance. You agree to send a light signal to your friend every second according to your own watch. As you descend deeper into the gravitational well, your friend notices something strange. The interval between your signals begins to grow. Instead of arriving every second, they arrive every 2 seconds, then every minute, then every hour. From your friend's perspective, you are moving in extreme slow motion. As you reach the very edge of the event horizon, your motions seem to freeze entirely. To the outside observer, you never actually cross the boundary, you simply become frozen in time, your image slowly fading and shifting to red as the light struggles to escape the immense gravity. Yet, from your own perspective, inside the spaceship, nothing has changed. Your watch ticks normally. You feel no slowing down. You cross the event horizon without noticing anything unusual at that precise moment. However, if you were to look back at the universe you left behind, you would see something equally extraordinary. You would see the cosmos aging in fast forward. Stars would be born, live out their lives, and die in mere moments. You would witness eons of cosmic history passing by in the blink of an eye. Black holes, therefore, are natural time machines, albeit ones that only allow travel into the future. They shatter our intuitive notion of a universal now. They teach us that time is not absolute and rigid, but elastic and relative, molded by the distribution of matter and energy. By studying how black holes manipulate time, we gain crucial insights into the fundamental structure of the universe, realizing that our experience of the passage of moments is entirely dependent on where we stand in the great gravitational landscape of the cosmos. This profound warping of time is not an isolated phenomenon. It is intimately woven into the very fabric of the cosmos, a fabric that Einstein showed us is a unified entity of space-time. The same immense gravity that can stretch a single second into an eon must also bend and twist the 3 dimensions of space. When light, the fastest thing in the universe, travels through this warped space, its path is no longer straight. This leads us to number 15. Gravitational lensing. A cosmic telescope. One of the first and most famous predictions of Einstein's general relativity was that the gravity of a massive object could bend the path of light. This was famously confirmed in 1919 during a solar eclipse, when astronomers observed that the light from distant stars passing near the sun was indeed deflected, just as Einstein had calculated. But the sun, massive as it is a gravitational lightweight compared to a black hole. A black hole, with its mass concentrated into an incredibly small region, creates a gravitational curvature so extreme that it acts as the universe's most powerful natural lens. This phenomenon is known as gravitational lensing. Imagine a distant galaxy, shining its light out in all directions. If a massive black hole happens to lie directly between us and that galaxy, the light from the galaxy that would have otherwise missed us is bent and refocused toward Earth. The black hole acts like a giant cosmic magnifying glass. This effect allows us to do something extraordinary. It allows us to see objects that are too far away and too faint to be detected with even our most powerful telescopes. The black hole's gravity gathers and amplifies the light, giving us a magnified view of the very early universe. This has enabled astronomers to study the first generations of galaxies, objects whose light has been traveling for over 13 billion years to reach us, providing a precious window into the cosmic dawn. The visual results of this lensing can be spectacular and surreal. If the alignment isn't perfect, the light from the background object can be distorted into multiple arcs and smudges around the foreground black hole. We might see 2, 3, or even 4 distinct images of the same single distant quasar. If the alignment is perfect, the light is smeared into a complete circle, a beautiful and ghostly halo known as an Einstein ring. These lensed images are more than just cosmic curiosities. By analyzing the precise shape, position, and brightness of these distortions, scientists can work backward to calculate the mass of the object doing the lensing. This has become one of the most powerful methods for weighing black holes and mapping the distribution of matter, both visible and invisible, across the cosmos. It allows us to probe the unseen, using the universe's own light as a cosmic surveyor's tool, all thanks to the profound way black holes bend the straight lines of space-time into graceful, illuminating curves. We have seen how the immense gravity of a black hole can act as a lens, bending the path of light across billions of light years. But this gravitational influence runs even deeper. It does not merely alter light's direction, it saps the very energy of light as it struggles to climb out of the gravitational abyss. This profound effect brings us to number 14. 14. Gravitational redshift. Light's uphill battle. Imagine tossing a ball into the air. As it travels upward, it fights against Earth's gravity, losing speed until it momentarily stops and falls back down. In a sense, light trying to escape from a massive object undergoes a similar, though more subtle, struggle. Light cannot slow down, its speed is constant. So instead of losing speed, it loses energy. For light, a loss of energy manifests as an increase in its wavelength. As the wavelength of visible light gets longer, it shifts toward the red end of the spectrum. This phenomenon, predicted by Einstein's theory of general relativity, is called gravitational redshift. It is the signature of light's uphill battle against the curvature of space-time. Just like with time dilation, this effect is present in weak gravitational fields as well. Light leaving the surface of the sun is very slightly redshifted by the time it reaches Earth. But around a black hole, this effect is magnified to an incredible degree. The hill that light has to climb is almost infinitely steep. Consider an atom in the hot accretion disk swirling just outside the event horizon. It emits a photon of a very specific color, a specific wavelength, based on its atomic properties. But for that photon to reach our telescopes far away in the universe, it must expend a tremendous amount of energy climbing out of the black hole's immense gravitational well. By the time this light reaches us, its wavelength has been stretched dramatically. A photon that was originally emitted as high-energy ray light might arrive at our detectors as low-energy radio waves. The light has been severely redshifted, carrying with it a clear message about the intensity of the gravity it just escaped. At the event horizon itself, this effect becomes absolute. The gravitational redshift becomes infinite. Any light emitted precisely at this boundary would have to expend all of its energy to escape, essentially stretching its wavelength to infinity, rendering it undetectable. This is, in a very real sense, why the event horizon marks the point of no return. Astronomers use this effect as a powerful diagnostic tool. By measuring the amount of redshift in the light coming from the material orbiting a black hole, they can map the gravitational field with incredible precision. It allows them to probe the very edge of the abyss and test the predictions of general relativity in an environment where space-time is stretched to its absolute limit. Gravitational redshift is the universe's own color-coded map of gravity's power. The stretching of light's wavelength, its gravitational redshift, gives us a powerful measure of a black hole's static gravitational pull. But most things in the universe are not static, they spin. And when a black hole spins, it doesn't just curve the space-time around it. It actively drags the very fabric of reality along for the ride. This bizarre and powerful phenomenon brings us to number 13, frame dragging. A space-time vortex. Einstein's general relativity reveals a universe far stranger than we could have imagined. One of its most mind-ending predictions is that a massive, rotating object should twist the space-time in its vicinity. This effect is known as frame dragging or the lens-thirring effect. To visualize this, imagine placing a heavy boiling ball into a thick vat of honey. If the ball is still, the honey around it is undisturbed. But if you spin the ball, the honey closest to it will be dragged along, creating a small whirlpool. The honey further away will be dragged less, and the honey at the edge of the vat might not move at all. Now, replace the bowling ball with a spinning black hole and the honey with the fabric of space-time itself. The black hole's rotation creates a cosmic vortex, a whirlpool of space-time that swirls relentlessly. Near a gently spinning object like the Earth, this effect is almost imperceptibly small. It was, however, successfully measured by the Gravity Probe satellite, which used 4 of the most perfectly spherical objects ever created by humanity to detect this tiny twist in our local space-time, confirming Einstein's prediction with stunning accuracy. But around a rapidly spinning black hole, frame dragging is a force of unimaginable power. It creates a region outside the event horizon known as the ergosphere. Within this region, space-time is being dragged around at a speed greater than the speed of light. This has a profound consequence. Inside the ergosphere, it is physically impossible to stand still. No matter how powerful your rocket engines are, you are forced to move in the direction of the black hole's spin. Space itself is moving faster than you could ever hope to travel against it. This swirling vortex is not just a theoretical curiosity. It has real, observable consequences. The accretion disks of matter spiraling into black holes are twisted and warped by this effect. It is also believed to be the engine that powers the colossal jets of plasma that we see blasting out from the poles of some black holes. The frame-dragging effect can twist the magnetic fields in the accretion disk into a tight coil, creating a powerful mechanism that flings matter and energy across thousands of light years. Furthermore, the physicist Roger Penrose theorized that this spinning energy could, in principle, be extracted. An advanced civilization could potentially throw an object into the ergosphere, split it in two, and have one part fall into the black hole while the other escapes with more energy than the original object had. In this way, the rotational energy of the black hole itself could be harvested. Frame-dragging transforms our image of a black hole from a passive cosmic sinkhole into a dynamic, powerful engine, cosmic whirlpool that actively shapes its environment. The swirling vortex of space-time created by a spinning black hole is a testament to the dynamic nature of gravity. But what happens when two of these cosmic whirlpools, two of these behemoths, are drawn together by their mutual attraction? The result is not a quiet merger, but the most violent event imaginable in the cosmos, an event that shakes the very foundations of reality. This cataclysm brings us to number 12. Gravitational waves, the sound of space-time. For a century after Einstein first proposed his theory of general relativity, one of its most profound predictions remained unproven. The theory suggested that space-time is not a static backdrop, but an active, flexible medium. It predicted that when massive objects accelerate through space-time, they should create ripples, waves of gravitational energy that propagate outward at the speed of light. These are gravitational waves. You can think of it like dropping two bowling balls into a still pond. As they circle each other and finally plunge together, they create waves that spread across the surface. Now, imagine this happening not on a two-dimensional surface, but in the four-dimensional fabric of space-time and with objects billions of times more massive than our Sun. The collision of two black holes is the ultimate cosmic cataclysm, an event that creates a veritable storm in space-time. In the final moments before they merge, the two black holes are orbiting each other at a significant fraction of the speed of light. They are tremendously massive objects moving incredibly fast in an extremely curved region of space-time. This violent acceleration churns the fabric of reality, sending out powerful gravitational waves that travel across the universe. For a fraction of a second, the energy released by this merger in the form of gravitational waves can outshine the combined light of all the stars in the observable universe. For decades, these waves were purely theoretical. Their effects were predicted to be so infinitesimally small by the time they reached Earth that detecting them seemed impossible. A passing gravitational wave would stretch and squeeze the space we inhabit by a distance smaller than the width of a proton. But human ingenuity prevailed. Using incredibly sensitive laser interferometers, the LIGO and Virgo collaborations built detectors capable of measuring these minuscule distortions. And on September 14, 2015, history was made. For the first time, we directly detected a gravitational wave. The signal was a perfect chirp, the sound of two black holes, each about 30 times the mass of the Sun, spiraling into each other a billion light-years away. We had heard the sound of space-time itself. This discovery was revolutionary. It opened a completely new window on the universe, a new sense with which to perceive the cosmos. Before gravitational waves, all of astronomy was based on light. But many of the universe's most dramatic events, like the merger of two black holes, happen in complete darkness. Gravitational waves allow us to listen to these hidden events. They are the ultimate confirmation of Einstein's dynamic theory of space-time and provide an unprecedented tool to probe the properties of black holes, testing our theories with every new cosmic chirp we detect. The cosmic chirps detected by LIGO and Virgo were more than just proof of gravitational waves. They were the echoes of specific, violent events. And like a sound carrying information about its source, these signals carried a detailed story about the objects that created them. When scientists deciphered that story, they found a surprise, a new mystery about the very stars that litter our universe. This brings us to number 11. Stellar graveyards, rewriting the lives of stars. For a long time, our understanding of how black holes were born seemed relatively straightforward. We believed they were the final stage in the life of the most massive stars. A star, many times more massive than our Sun, would burn through its nuclear fuel over millions of years. When the fuel ran out, the star's own immense gravity would cause its core to collapse catastrophically, triggering a spectacular supernova explosion that would blast its outer layers into space. The crushed remnant left behind would be a stellar, black hole. Based on our models of how these massive stars live and die, We had a good idea of what to expect. We predicted that these stars would shed a significant amount of their mass during their lifetimes through powerful stellar winds, long before they ever exploded. Therefore, we expected that the resulting black holes would typically be in the range of 5 to perhaps 15 times the mass of our Sun. Then we started listening to the universe with gravitational waves. The very first merger detected, the event that changed astronomy forever, was the collision of two black holes that were roughly 29 and 36 times the mass of the Sun. This was a genuine shock. How could such massive black holes even exist in a binary pair? Our standard models of stellar evolution struggled to produce them. This single detection, and the many that followed, forced us to go back to the drawing board and rethink the final, dramatic chapters of a star's life. Black holes, the endpoints of stellar evolution, became the key to unlocking the processes that led to them. The solution to this puzzle appears to lie in the star's environment and its chemical makeup. Astronomers now believe that these massive black holes are born from stars that formed in pristine, low metallicity environments. In astronomy, metals are any elements heavier than hydrogen and helium. Stars born in the early universe or in small dwarf galaxies had very few of these heavy elements. It turns out that these heavy elements are a key ingredient in driving powerful stellar winds. Therefore, a massive star with very low metallicity would have much weaker winds throughout its life. It would hold on to much more of its original mass. When it finally reached the end of its life and collapsed, there was simply more material left over to form a much more massive black hole, exactly like the ones LIGO and Virgo were detecting. By studying the masses of merging black holes, we are essentially performing cosmic archaeology. We are looking at a stellar graveyard and learning about the lives of the stars that are buried there. These dark, silent remnants are telling us a new and more complete story about how stars evolve, how they interact with their surroundings and how they die, forcing us to rewrite the textbooks on the life cycle of the cosmos. The graves of stars, revealed by gravitational waves, have forced us to rewrite the story of how individual black holes are born. But these stellar, as objects, even at 50 times the mass of our Sun, are mere pebbles compared to the mountains that lurk in the centers of galaxies. The existence of these giants presents us with one of the greatest chicken and egg problems in all of cosmology. This leads us to number 10. Supermassive seeds, the origin of cosmic monsters at the heart of our own Milky Way, and indeed at the center of nearly every large galaxy we have ever observed, lies a supermassive black hole. These are not the remnants of a single star, but cosmic behemoths with masses ranging from millions to tens of billions of times that of our Sun. Their origin is a profound and unsolved mystery. The problem is one of time. When we look deep into the universe with telescopes like the Hubble and the James Webb Space Telescope, we are looking back in time, and we can see that these supermassive black holes were already in place very early in cosmic history, less than 1 billion years after the Big Bang. They are ancient. This presents a serious puzzle. How did they get so big, so fast? A normal stellar, as black hole, born from the first generation of stars, would have to grow at an almost impossible rate to reach such a colossal size in such a short amount of time. Even if it had a constant supply of gas and stars to consume, there is a physical limit to how fast a black hole can feed, known as the Eddington limit. Trying to grow a supermassive black hole from a single star in the early universe is like trying to fill an entire lake with a garden hose in just a few minutes. It simply doesn't add up. This has led scientists to theorize that the universe must have had a way to create massive seeds for these black holes to grow from. There are several competing ideas for what these seeds might have been. One theory proposes the existence of direct collapse black holes. In the very early universe, vast, primordial clouds of pure hydrogen and helium gas unpolluted by heavier elements could have become so massive and dense that they bypassed the star formation phase entirely and collapsed directly into a black hole of maybe 100,000 solar masses. This would give them a significant head start. Another, more exotic idea suggests the seeds were primordial black holes, objects that didn't form from stars at all but were instead forged in the chaotic, ultra-dense conditions of the very first moments after the Big Bang itself. A third possibility is a runaway process in the heart of the first dense star clusters. In this scenario, the first stars form, live fast and die young, leaving behind a swarm of black holes. These black holes would sink to the center of the cluster and begin to merge with each other in a rapid, higher chain of collisions, quickly building up a much larger object. Unlocking this mystery is one of the primary goals of modern astrophysics. By hunting for intermediate, as black holes, the missing link between stellar, as and supermassive, and by peering ever further back in time to witness the birth of the first galaxies, we are searching for the evidence that will tell us which of these scenarios is correct. The supermassive black holes we see today are the final chapter of a story whose first page is still unwritten. Finding their seeds is to find the origin story of the cosmic ecosystems we call galaxies. The puzzle of where these supermassive giants came from is deeply intertwined with another, equally profound question: what is their purpose? It turns out these cosmic monsters are not just passive anchors sitting at the center of their galaxies. They are active participants, cosmic gardeners that shape and regulate the growth of their entire galactic homes. This intimate relationship brings us to number 9. Galaxy coevolution, the cosmic thermostat. For many years, astronomers pictured galaxies as majestic, self-contained islands of stars, with the supermassive black hole at the center being little more than a gravitational afterthought, cherry on top. But as our observations became more precise, a startling pattern emerged. Scientists discovered a remarkably tight correlation between the mass of a galaxy's central black hole and the properties of the galaxy's central region, known as its bulge. Specifically, the bigger the black hole, the more massive the bulge and the faster the stars within it are moving. This relationship holds true across a vast range of galaxy sizes, from small ones to the largest elliptical galaxies in the universe. This is a profound clue. It's like finding a strong correlation between the size of a tree's roots and the size of its branches. It strongly suggests that the two did not grow in isolation, but that their growth is somehow linked. The black hole and its host galaxy must have evolved together, a process known as coevolution. But how can an object confined to the very central core of a galaxy, a region smaller than our solar system, possibly influence a structure that spans 100,000 light years? The answer lies in a process called feedback. When a supermassive black hole is actively feeding, the gas and dust swirling into it form a super-heated, incredibly bright accretion disk. This furiously shining object, known as an active galactic nucleus or a quasar, can become so luminous that it outshines the entire host galaxy combined. This immense torrent of radiation acts like a cosmic super wind, blasting outward through the galaxy. In addition, as we've seen, many of these active black holes launch colossal jets of particles from their poles at nearly the speed of light. These jets plow through the interstellar medium of the galaxy, carrying tremendous energy. Both of these processes, the radiation from the accretion disk and the power of the jets, heat up the gas throughout the galaxy. They can even blow the gas clear out of the galaxy and into intergalactic space. This is critically important because stars are born from vast, cold clouds of gas. If all the gas in a galaxy is heated up or removed, star formation grinds to a halt. This creates a beautiful self-regulating feedback loop. A young galaxy has plenty of cold gas, which fuels both star formation and the growth of the central black hole. As the black hole grows and feeds more voraciously, it becomes more active and powerful. Eventually, it becomes so powerful that its energy output effectively shuts off its own food supply by expelling the gas from the galaxy. The black hole's growth stops, and with the gas gone, the galaxy's ability to form new stars also ceases. This single mechanism elegantly explains the tight correlation we observe. The black hole is the galaxy's central thermostat. It regulates its own growth and, in doing so, dictates the ultimate size and fate of its host galaxy. It tells us that to understand how galaxies came to be, you cannot ignore the monster at their heart. The supermassive black hole, acting as its galaxy's central thermostat, is a powerful force of regulation, capable of shutting down star formation across thousands of light years. But these immense outflows, these galactic winds and jets, are not just empty blasts of energy. They are rivers of matter, and the contents of that matter are vital to our own existence. This role as a cosmic distributor brings us to number 8. The galactic fountain, seeding the cosmos with life's ingredients. The universe, in its infancy, was a remarkably simple place. The Big Bang forged only the lightest elements: hydrogen, helium, and a trace amount of lithium. Every other element on the periodic table, the carbon in our bodies, the oxygen we breathe, the silicon in the rocks beneath our feet, and the iron in our blood, was created later, forged in the fiery hearts of stars and blasted into space when those stars died in supernova explosions. Stars are the element factories of the cosmos. But creating the elements is only half the story. For these vital ingredients to be used, they must be mixed and distributed throughout their host galaxy, seeding the next generation of stars and planets. If all the heavy elements created in the dense, star-rich center of a galaxy remained locked there, the outer regions would remain barren, unable to form rocky planets or the complex chemistry required for life. This is where the supermassive black hole plays a surprising and creative role. The same powerful feedback mechanisms that regulate star formation also act as a galactic fountain, a cosmic distribution network for the building blocks of life. As stars live and die near the galactic center, they enrich the surrounding gas with the heavy elements they have forged. This element, rich gas, is then swept up by the intense winds blowing from the black hole's accretion disk, or it is captured and funneled into the colossal jets. These outflows then blast this precious cargo high out of the galactic disk, sometimes tens of thousands of light years into the vast, diffuse halo of the galaxy. This material does not escape forever. Over millions of years, the galaxy's gravity will pull this enriched gas back in. It rains back down onto the galactic disk like a slow, metallic drizzle, far from where it originated. This process thoroughly mixes the elements across the galaxy, ensuring that even new stars forming in the quiet outer suburbs have access to the materials needed to build planets like Earth. Furthermore, the extreme conditions within the accretion disk itself, the immense temperatures, pressures, and magnetic fields, constitute an even more exotic element factory. Some theories suggest that certain rare, heavy elements could be synthesized in this swirling vortex in a way that is not possible even in the core of a star. The supermassive black hole, therefore, is not just a destructive force or a passive anchor. It is an active and essential part of the galaxy's circulatory system. It is the engine that drives the great cosmic recycling program, taking the ashes of dead stars and distributing them as the seeds for new worlds. It helps ensure that the universe is not just filled with stars, but with the potential for complexity, for chemistry, and for life. We have seen how the supermassive black hole, through its powerful outflows, acts as a galactic fountain, distributing the essential, life-giving elements forged in stars. This paints the picture of a creative force, enriching its domain. But the story of its influence on star birth is even more complex and surprising, a tale of cosmic duality. This brings us to the intricate balance of number 7. Triggering star formation, a creative destruction. We have just established that the immense energy pouring from an active black hole can heat up and blow away the cold gas needed for stars to form, effectively acting as a galactic off switch. This is known as negative feedback. But nature is rarely so simple. It is now becoming clear that for every destructive action of a black hole, there can be a creative and opposite reaction. The very same outflows that can quench star formation in one area can, in another, become the powerful trigger that ignites it. This is positive feedback. To understand this, we must picture the interstellar medium, the vast expanse between the stars. It is not empty, but is filled with enormous, tenuous clouds of gas and dust. For a new star to be born, a dense pocket of this gas must collapse under its own gravity. However, these clouds are often too diffuse and warm. The internal pressure of the gas pushes outward, perfectly balancing the inward pull of gravity, resulting in a stable stalemate that can last for millions of years. The cloud needs a push, a shockwave, to kickstart the process, and a supermassive black hole can provide the most powerful push in the universe. When the colossal jets and winds from the black hole slam into one of these vast, stable gas clouds, they create immense shockwaves. Like a cosmic snowplow, the leading edge of the outflow compresses the gas, piling it up and dramatically increasing its density. In this moment of violent compression, the stalemate is broken. Gravity suddenly overwhelms the gas pressure and pockets of the cloud begin to collapse uncontrollably, fragmenting into hundreds or even thousands of dense cores, each one the seed of a brand new star. Astronomers have witnessed this process in action. Using powerful telescopes, they have observed chains of brilliant, newborn stars lighting up along the path of a black hole's jet, like streetlights being switched on down a long road. They see stellar nurseries being formed on the compressed edges of gigantic bubbles blown by galactic winds. In these instances, the black hole is not the enemy of star formation, but its direct progenitor. This reveals a far more nuanced and beautiful picture of the black hole's role. It is a cosmic sculptor of its galaxy, possessing a dual nature. In the dense, chaotic galactic core, its power can be sterilizing, preventing new stars from forming. But further out, as its energy expands and collides with the galaxy's raw materials, that same power can become a generative force, birthing entire new clusters of stars. It demonstrates the intricate and delicate balance that governs the cosmos, where the same force can be responsible for both an ending and a new beginning. The dual nature of a black hole, capable of both creating and destroying star-forming regions, showcases its profound influence on the visible matter within its galaxy. But the visible matter, the stars, the gas, the dust, is only a tiny fraction of the cosmic inventory. The universe, we have discovered, is dominated by a mysterious, invisible substance that holds galaxies together. And in our search for this substance, black holes present a tantalizing, if controversial, possibility. This leads us to number 6, the dark matter enigma. Primordial black holes. One of the most profound and humbling truths of modern cosmology is that we do not know what most of the universe is made of. When we observe how galaxies rotate and how they are clustered together in great cosmic webs, we see that there is far more gravitational pull than can be accounted for by the stars and gas we can see. There must be an invisible mass, a cosmic scaffold upon which our luminous universe is built. We call this substance dark matter, and it outweighs all normal matter by more than 5 to 1. For decades, the leading candidates for dark matter have been hypothetical, undiscovered subatomic particles. But what if the answer is not a new particle, but an old and familiar concept? What if dark matter is simply made of black holes? These would not be the black holes born from the death of massive stars. Those are far too rare to account for the sheer abundance of dark matter. Instead, the theory points to a much more ancient and exotic type, primordial black holes. As the name suggests, these are black holes that would have been forged not in the hearts of dying stars, but in the chaotic, ultra-dense and turbulent conditions of the very first second after the Big Bang. In that primordial inferno, tiny fluctuations in the density of the universe could have been so extreme that some regions collapsed directly into black holes, long before the first stars ever existed. These primordial black holes could have been created with a vast range of masses, from smaller than an asteroid to many times the mass of our Sun. They are an almost perfect dark matter candidate. They are massive, they exert a powerful gravitational pull, and, being black holes, they are inherently dark and do not interact with light. They are an elegant solution because they don't require the invention of new physics or new particles. They are a natural, albeit unproven, consequence of our existing understanding of gravity and the early universe. The hunt for these ancient relics is one of the most exciting frontiers in physics. One method is through gravitational microlensing. If a primordial black hole were to pass directly between us and a distant star, its gravity would briefly act as a lens, causing the star to brighten in a characteristic way. Large-scale surveys have been searching for these events for years, and while they haven't found a definitive signal, they have helped to rule out certain mass ranges. An even more exciting prospect lies with gravitational waves. If these primordial black holes exist, they should occasionally find each other in the dark void of space and merge. Our gravitational wave detectors could potentially hear the chirps from these ancient collisions, providing a smoking gun for their existence. Each new signal we detect is scrutinized for clues that it came not from the collapse of a star, but from an echo of creation itself. Finding them would solve one of the deepest mysteries in science, revealing that the invisible ghost that haunts our cosmos is made from the oldest and darkest objects in existence. While the possibility that ancient black holes constitute the universe's dark matter would be a staggering revelation, it only addresses one half of the dark problem. The other half is arguably even more mysterious, a pervasive force that is actively shaping the ultimate fate of our cosmos. And once again, at the heart of this enigma, we may find the unexpected influence of black holes. This leads us to the revolutionary idea at number 5. The source of dark energy, driving the universe apart. In the late 1990s, astronomers made a discovery that shook the foundations of cosmology. They found that the expansion of the universe is not slowing down, as had been expected, due to the gravitational pull of all the matter within it. Instead, the expansion is accelerating. The universe is flying apart at an ever-increasing rate, pushed by a mysterious, repulsive force that permeates all of space. We have given a name to the source of this acceleration: dark energy. Dark energy is the single, most dominant component of our universe, making up nearly 70% of its total energy density. Yet, we have almost no idea what it is. In our standard model of cosmology, it is represented by a term called the cosmological constant, a kind of intrinsic energy of empty space itself. But this is more of a placeholder than an explanation. It doesn't tell us where this energy comes from. Now, a stunning new theory proposes an answer that is as elegant as it is profound. What if black holes themselves are the source of dark energy? This idea stems from a deep theoretical connection between gravity and thermodynamics, suggesting that black holes contain vacuum energy in their cores, the very same kind of energy proposed to be the cosmological constant. The revolutionary part of the theory is how these black holes interact with the universe. It suggests that black holes are not just growing by consuming matter, but that their mass is also increasing through a process called cosmological coupling. In essence, they grow in mass as the universe itself expands. This would be a fundamental paradigm shift. It means the energy stored within black holes does not get diluted as the universe expands, unlike normal matter. As space gets bigger, the black holes also get bigger, and their total energy contribution grows in a way that perfectly mimics the behavior of dark energy. They provide a constant outward push, a cosmic anti-gravity that drives the accelerating expansion. The most compelling piece of evidence for this idea is a simple calculation. When researchers took our best estimates of the population of black holes in the universe and calculated the combined vacuum energy that would be stored inside them according to this theory, the number they got was astonishingly close to the measured value of dark energy. For the first time, we may have a physical source for the universe's dominant energy component, rooted in objects we can actually observe. If this theory proves correct, it would be one of the most important discoveries in the history of science. It would mean that black holes are not merely the final, quiet endpoints of stellar evolution. They are the active, dynamic engines that dictate the ultimate destiny of our cosmos. It would mean that the same objects that create the deepest pockets of gravity are also, paradoxically, the source of the force that is pushing everything apart. The idea that black holes are the very engines driving the accelerated expansion of the cosmos is a staggering one. It elevates them from mere cosmic curiosities to the primary architects of the universe's ultimate fate. But this profound theory does not just solve the mystery of why the universe is expanding faster. In a beautiful piece of cosmic synergy, it may also solve a deep and troubling paradox concerning the precise rate of that expansion. This brings us to the crucial puzzle at number 4. The Hubble tension. Unifying the cosmic ruler for nearly a century, we have known that our universe is expanding. The great cosmic challenge has been to measure exactly how fast. This rate of expansion is known as the Hubble constant, and it is arguably the most important number in all of cosmology. Knowing its precise value tells us the size, age, and ultimate fate of our universe. The problem is, when we use our two most precise methods to measure it, we get two different answers. This disagreement, known as the Hubble tension, has become one of the most significant crises in modern physics. On one hand, we can measure the Hubble constant by looking at the very early universe. We do this by studying the cosmic microwave background, or CM, which is the faint afterglow of the Big Bang. The incredible data from the Planck satellite allows us to see tiny temperature fluctuations in this ancient light. By feeding these measurements into our standard model of cosmology, we can predict what the expansion rate should be today. This method gives us a very precise value. On the other hand, we can measure the expansion rate directly by looking at the local or more recent universe. We do this by building a cosmic distance ladder. We measure the distances to nearby galaxies using pulsating stars called Cepheids, and then use those galaxies to calibrate the brightness of a special type of exploding star, a Type Ia supernova. Because these supernovae always explode with roughly the same intrinsic brightness, we can use them as standard candles to measure distances to the far reaches of the cosmos. When we use this method, we also get a very precise value for the Hubble constant. Here is the tension. The two values do not agree. The measurement from the local universe suggests the cosmos is expanding about 9% faster than the value predicted from the early universe. The error bars on these measurements are now so small that a simple mistake can no longer be the explanation. It means our standard model of cosmology, the very foundation of our understanding of the universe, is missing something fundamental. This is where the new theory of black holes as the source of dark energy provides a stunningly elegant solution. The standard model of cosmology has always treated black holes as gravitationally inert, their masses remaining constant unless they swallow matter. But in the cosmologically coupled model we just discussed, black holes gain mass simply because the universe is expanding. This has a crucial effect that is not accounted for in our current calculations. In the early universe, before the first stars had formed, there were no stellar black holes. So, our measurement from the cosmic microwave background is unaffected. But in the later universe, billions of years of star formation and death have filled the cosmos with a vast population of black holes. As these black holes have grown in mass through cosmological coupling, their collective gravitational influence has subtly increased over time. This extra unaccounted for gravity, particularly inside galaxies, where supernovae explode, alters our measurement. It means the supernovae we are using as standard candles are not quite as standard as we thought. When we correct our distance calculations to include the effect of this black hole growth, the value of the Hubble constant derived from the local universe is adjusted downwards. It comes into perfect, beautiful agreement with the value predicted from the early universe. The tension vanishes. If this holds true, black holes have solved the greatest paradox in modern cosmology. They are the missing ingredient in our cosmic recipe, the key that synchronizes our understanding of the universe, beginning with our observations of its present, creating a single unified story of cosmic evolution. The idea that black holes can solve the Hubble tension is a profound one. It weaves their existence into the grand tapestry of cosmic evolution, from the Big Bang to the present day. But the tapestry of space-time itself may hold even deeper secrets that black holes might not just influence, but actively unlock by offering a passage through the very fabric of reality. This brings us to the tantalizing possibility at number 3. Wormholes, gateways through space-time. Within the mathematical framework of Einstein's general relativity lies a concept so extraordinary that it has fueled science fiction for generations: the wormhole. The theory suggests that a black hole is not just a one-way street to a point of infinite density. It could, in principle, be one end of a tunnel through space-time, a cosmic shortcut known as an Einstein-Rosen bridge. The other end of this bridge would be a white hole, a theoretical, time-reversed cousin of a black hole from which matter and energy would gush out. This is the ultimate cosmic shortcut. Instead of traveling for millions of years across the vast emptiness of space to reach a distant star, a wormhole could provide a direct tunnel, allowing you to traverse that immense distance in a matter of moments. It's the difference between traveling all the way around a mountain and simply walking through a tunnel that cuts straight through its center. However, the universe is not so simple. The initial calculations showed that these natural wormholes would be hopelessly unstable. The throat of the tunnel would pinch off and collapse into a singularity so quickly that not even a beam of light, the fastest thing in the universe, would have time to make it through. Any traveler attempting the journey would be crushed in the collapsing tunnel long before they reached the other side. For a wormhole to be traversable, something would need to prop its throat open, to fight against the immense gravitational forces trying to close it. The physics for this is highly speculative, but it points to the need for a truly bizarre substance known as exotic matter. This is not matter in any sense we know it. It would have to possess negative energy density, a property that would allow it to exert a kind of gravitational repulsion, effectively acting as an anti-gravity scaffold to keep the tunnel open. We have never directly observed such matter, but there are hints in the strange world of quantum mechanics, such as the Casimir effect, that negative energy states are not entirely forbidden by the laws of physics. If such matter could exist, and if it could be harnessed, then creating and sustaining a traversable wormhole might shift from the realm of impossibility to the realm of extreme, but conceivable, engineering. The implications of this are almost beyond comprehension. A stable wormhole would not only provide a shortcut across our own universe. Depending on the geometry of the connection, could potentially be a gateway to another universe entirely, a bridge to a separate reality with its own stars, its own galaxies, and perhaps even its own different laws of physics. Black holes, in this scenario, are no longer just the final graves of stars. They become potential doorways. They challenge our most fundamental notions of distance, travel, and connectivity. The study of their extreme gravity forces us to confront these radical possibilities, to ask whether the space between the stars is the only path available, or whether, hidden within the darkest shadows of the cosmos, there are gateways waiting to be opened. The speculation that black holes could be gateways to other places, or even other universes, is a profound leap for the human imagination. It takes them from being cosmic endpoints to potential new beginnings. But one theory takes this concept a step further, suggesting that a black hole is not merely a tunnel to another place, but the very seed of a new creation, a new cosmos in its own right. This brings us to the astonishing idea at number 2. Cosmic reproduction, the birth of baby universes. We return to the singularity, that point at the heart of a black hole where our physics breaks down. Our current theories tell us it is a point of infinite density, but many physicists believe this is simply a sign that our theories are incomplete. What if, instead of a final, crushing end, the singularity represents a moment of cosmic rebirth? A fascinating and speculative theory known as cosmic natural selection, proposed by physicist Lee Smolin, suggests that every time a black hole forms, a new universe is born. According to this idea, when matter collapses to the point of singularity, it doesn't just stop, it bounces. The immense concentration of matter and energy could trigger a new Big Bang, not within our space-time, but creating an entirely new, expanding bubble of space-time that is causally disconnected from our own. This new baby universe would exist on the other side of the singularity, forever inaccessible and invisible to us. This concept alone is mind-ending, but the theory goes one step further, offering a potential explanation for one of the deepest mysteries of our existence, the fine-tuning problem. The fine-tuning problem refers to the observation that the fundamental constants of nature, things like the strength of gravity, the mass of the electron, the value of the cosmological constant, seem to be exquisitely and precisely tuned to the values needed for a complex, stable universe with stars, galaxies, and ultimately, life to exist. If any of these constants were even slightly different, the universe would be a barren, empty place. Why is our universe so perfect? Cosmic natural selection offers a stunning answer. It suggests that when a baby universe is born from a black hole, its fundamental constants are not exactly the same as its parent universes. There are tiny, random mutations. Now, consider this in an evolutionary context. Which universes will have the most offspring? The answer is simple. The universes that are best at making black holes. A universe whose constants were hostile to the formation of large stars would produce few, if any, black holes, and therefore would have very few, if any, baby universes. It would be a cosmic dead end. But a universe like ours, whose laws are perfectly suited for creating vast numbers of massive stars that live, die, and collapse into black holes, would be incredibly fertile. It would spawn countless new universes, each with slightly mutated constants. Over countless cosmic generations, this process of natural selection would favor those universes whose physics is optimized for producing black holes. It's no surprise, then, that we find ourselves in such a universe. The fact that it is also hospitable to life is simply a fortunate byproduct of a cosmos that has evolved to maximize its own reproduction. This theory transforms our understanding of black holes. They are no longer just the graveyards of stars within our universe. They are the engines of cosmic creation, the seeds of new realities. Our entire cosmos could be just one branch on an infinite cosmic family tree, a single descendant in a long line of universes, each born from the darkness at the heart of a star. The idea that our universe could be one of many, born from the heart of a black hole, is perhaps the most profound shift in cosmic perspective since we learned the Earth was not the center of all things. It suggests that black holes are not an end, but a beginning. And yet, there is one final mystery, one that underpins all the others we have discussed. To solve it would be to read the source code of reality itself. This is the ultimate prize, the final frontier, and it brings us to number one. The theory of everything, uniting the two pillars of physics throughout our journey. We have returned time and again to a single, fundamental conflict. It is the great, unresolved civil war at the heart of modern physics, the clash between our two most successful theories of the universe. On one side, we have Einstein's general theory of relativity, the majestic theory of the very large. It describes gravity as the graceful curvature of space-time and governs the orbits of planets, the structure of galaxies, and the expansion of the entire cosmos. On the other side, we have quantum mechanics, the spectacularly successful and bizarre theory of the very small. It governs the world of particles, probabilities, and forces that hold atoms together. Both theories have been tested to incredible precision in their own domains, and both work perfectly. But in certain extreme corners of the universe, these two great pillars of our understanding give us completely contradictory answers. And the single greatest arena where this conflict plays out, where both theories are pushed to their breaking points, is inside a black hole. General relativity tells us that at the center of a black hole lies a singularity, a point of infinite density and zero volume where the laws of physics cease to make sense. Quantum mechanics, however, abhors infinities. It suggests that at such small scales, space-time itself should have a grainy, quantum structure, preventing such a collapse. General relativity describes a smooth, placid event horizon, while quantum mechanics, through the work of Stephen Hawking, tells us this boundary must fizz and sparkle with quantum particles, leading to the information paradox that threatens to unravel the foundations of science. This is not a minor disagreement. It is a signpost pointing to a deeper, more fundamental truth. It tells us that both of these theories, as brilliant as they are ultimately just approximations of a single, underlying theory that unites them both. This undiscovered theory is the holy grail of modern physics, a theory of everything, more formally known as a theory of quantum gravity. Such a theory would be the final chapter in the story that began with Newton. It would describe the fundamental nature of space, time, matter, and energy from a single set of principles. It would explain what happens at the moment of the Big Bang and at the heart of a black hole. It would resolve the information paradox and tell us what truly lies beyond the event horizon. And black holes are our only guide. They are the universe's only laboratory where the effects of quantum gravity are magnified to a cosmic scale. Theories like string theory, which posits that fundamental particles are tiny vibrating strings, or loop quantum gravity, which suggests space-time itself is made of discrete, indivisible chunks, make different, testable predictions about the nature of black holes. Perhaps a black hole's singularity is replaced by a fuzzball of strings, or a Planck star that bounces back. Perhaps information is not lost, but is stored in a subtle quantum entanglement between the inside and the outside. The answers are hidden there, in the darkness. By studying these cosmic objects with ever greater precision, by analyzing the faintest ripples in space-time from their mergers, by imaging the precise shape of their shadows, by decoding the light from matter at the final moment before it plunges into the abyss, we are gathering the clues needed to build this ultimate theory. This is the greatest promise a black hole holds. It is more than a cosmic vacuum cleaner, more than a galactic engine, more than a gateway to other worlds. It is a Rosetta Stone. It is the place where the two great languages of our universe, relativity and quantum mechanics, are forced to speak to each other. By learning to translate, we may finally be able to read the single, elegant sentence that writes all of reality. And so, our journey through the cosmic darkness comes to an end. From the paradox of lost information to the hope of a final, unified theory, we have seen how black holes are not voids of emptiness, but crucibles of creation, engines of cosmic evolution and signposts pointing toward a new understanding of our universe. They are the ultimate expression of gravity's power, and in their depths lie the answers to the most profound questions we can ask. As you drift now into the quiet of the night, perhaps you will dream of these cosmic whirlpools, not as objects of fear, but as beacons of knowledge, their darkness illuminating the path to the very heart of reality.